Hello, it's GCSE Physics Explained. I'm going to go over a combined science, the physics part. It's a higher tier. Now, although this is higher tier, there's quite a lot of this will be relevant for the foundation tier as well, and indeed the triple. Right, let's get into it. Figure 1 shows 3 resistors, R1, R2 and R3, connected to a power supply. The current in R2 will always be, right, there's R2, what's our options? Less than the current in R1, less than the current in R3, the same as the current in R3, or the same as the current in R1. Now this is checking that you understand Kirchoff's law. So Kirchoff's law said what goes into a junction, let's call that current 1, must come out of the junction. Let's call that current 2 and current 3. Which is correct, because if 10 cars goes into a junction and 3 cars come out the top, then 7 cars must have came out the bottom. It's simple maths. So going through R1, we've got a large current. When it gets to this junction, some of it's going to split off and go this top path through R2, and some of it's going to go through R3. Now, we don't know how much is going to go through R2 because we don't know the size of this resistor or the size of this resistor. If R2 was the same size as R3, then I2 would be the same size as I3. But whatever's happening, I2, this current going through R2, is definitely going to be smaller than I1. So A is correct. The current in R2 will always be less than the current in R1. Part B. Figure 2 shows a power supply connected to a 82 ohm resistor and a variable resistor. The potential difference across the 82 ohm resistor is 6 volts. So potential difference just means the voltage. Calculate the current in the circuit. Okay, so we'll use Ohm's law, which is voltage equals current times by resistance. We can shorten that. So V equals I times by R. And we are trying to calculate the current, I. So if we use the magic triangle, create a top shelf, and this bottom section, split it up into 2 by putting a multiplication sign there. If you don't know how to use magic triangles, I've got a video that shows you how to use magic triangles. Just click the link above. I've got something times by something, so shove those things into the spaces. Something times by something, and I've got one thing left and one space, so shove that thing in that space. Now, just cover up what you're looking for, and what you're left with is how to work it out. So we're looking for I, cover up I equals V divided by R. Take the voltage, 6 volts, take the resistance, 82 ohms, and that pops out as 0.073 amps. Part 2. Describe how a student could add meters to the circuit so that the current in the 82 ohm resistor and the potential difference across the 82 ohm resistor can be measured. You may like to draw a new circuit diagram to help you with your answer. Right, just for speed, I'm just going to annotate it. So we need to put an ammeter into the circuit. Now that ammeter needs to be in series with the component that you're measuring. In series means it needs to be one after another after another. It's like a TV series, episode 1, then episode 2, and then episode 3. And a voltmeter needs to come in parallel, which means at the same time. So just create an extra loop and pop it across. And that's how we do it. If you don't know what all these symbols are, I've got a video for that. Shows you all the symbols and easy ways to remember them. Just click the link above. So how do we verbalise that? We say add an ammeter in series with the resistor and add a voltmeter in parallel across the resistor. The student replaces the 82 ohm resistor in the circuit with two different resistors as shown in figure 3. So they put a 68 ohm resistor in series with a 56 ohm resistor. The student adjusts the current to be 0.03 amps, so that's our I. Write down what you know when you know it. Calculate the total potential difference, so the total voltage, across the 68 ohm and 56 ohm resistors combined. So we'll use Ohm's law again, and Ohm's law is voltage equals current times by resistance. Now, we could do it separately. We could work out what the voltage is through this resistor and then add it to the voltage through this resistor. So that would look like this. Or, alternatively, when you've got resistors next to each other in series, which means one after the other, to get the total resistance, you just add them together. So these two resistors have got a combined resistance of 124 ohms. So we could just say that voltage equals current times by resistance, and this time we'll use the total resistance. So the current is still 0.03 amps, and this time we'll times it by 124 ohms, and that equals the same value, 3.72 volts. Question 2, part 1. Thermal energy is needed to change the state of a substance from solid to liquid. Calculate the thermal energy needed to change the state of 3.5 kilograms, so that's the mass, for mass, of a substance with a specific latent heat of 336,000 joules per kilogram. So latent heat, that's L. Use an equation selected from the list of equations at the end of this paper. Right. So we're looking for something with M and L in, and we're trying to calculate the thermal energy E. Or sometimes thermal energy is called Q. So we're looking for something with a Q, an M, and an L. There we are. Thermal energy for a change of state is mass times by specific heat capacity. Change of state, Q equals ml. Yeah, change the state. So energy, thermal energy, Q, equals the mass times by the specific latent heat. So that's 3.5 kilograms times by 336,000 joules per kilogram. And that equals 1176000. Or we could put that down, if we rounded it up, that's like 1.2, and that would be times 10 to the 6. Or if you didn't like rounding up like that, 1.18 times 10 to the 6. And that's joules. Personally, I very often at GCSE, I just write it in longhand. Part 2. Give one reason why the change of state from solid to liquid is described as a physical change. Well, basically it's because it's reversible. I haven't actually changed anything chemically. I could easily turn it from a liquid back into a solid simply by cooling it down. So I know it's only worth 1, but what if they use this similar question this year and it's worth 2? So you'd get 2 marks for putting them. Question B. The kinetic theory describes solids, liquids and gases in terms of particles. The table in figure 4 gives the density of various substances at room temperature. So substances, water, lead and air, and it tells us the density. Use the kinetic theory to explain, in terms of particles, the difference in the densities of lead and air. So, lead is basically a solid, and it's got a density of 11,300 kilograms per meter cubed. Water is a liquid, and it's only got a density of 1,000 kilograms per meter cubed. So you can see that lead is 11 and a bit, more times denser than water. And that is because when a substance is a solid, the particles are much closer together than when they're a liquid. So if it did ask you to draw what these particles look like, water, that's a liquid, so the particles would be close together, but they wouldn't really be in a nice neat structure. Lead is a solid, so the particles would be in nice neat rows, and air is a gas, so there wouldn't be very many particles at all, and they'd be moving very quickly, bouncing off the container walls. In a solid, all the particles can do is vibrate a little bit, and in water, which is a liquid, the particles can move past each other, but they don't move as fast as the particles in a gas. Part C. One of the steel nails, shown in figure 5, has a mass of 2.7 grams and a volume of 0.31 centimetres cubed. Calculate the density of the steel. So density is mass divided by volume. So that equals 2.7 grams divided by 0.31 centimetres cubed. And I've just left it in grams and centimetres cubed because that's what they want the units in, grams per centimetre cubed. And that equals 8.7 grams per centimetre cubed. Describe how the movement of particles in a substance changes as the substance is cooled down towards minus 273 degrees C. Okay, so what is the significance of minus 273 degrees C? That's what we call absolute zero. Now, Lord Kelvin, he said that as things get hotter, they get more energy, so they move more. So he wanted to find out, if things got colder, do they move less? And is there a point where it's so cold that particles don't move at all? As part of the kinetic theory, which we've just discussed in one of the previous questions. So describe how the movement of particles in a substance changes as the substances cool down. So as the substance gets cooled down, the particles do get less energy, so they do move less, and once they get down to minus 273, the speed of the particles would approach zero. In other words, no movement. Cooling causes particles to move less, so speed gets slower. Question 3. The student investigates how the extension of a spring changes when different weights are hung from one end. Figure 6 shows the student's apparatus. Right, we've got a retort stand here holding the thing up, got a ruler clamped on there, spring clamped on here, and a slotted weight hanging on the bottom. Which diagram correctly shows the forces acting on this spring? Right, well, the slotted weight is going to be acting down, so that one's wrong straight away. And the spring's going to be pulling upwards, so that one's wrong. Right, so we just need to decide, is it A or D? That's correct. Well, where the slotted weight is pulling down from, that's fine, and that's actually fine as well. But the spring will be pulling from the top part up here, where it's connected, rather than down here. So your answer is A. Question B. Figure 7 is a graph showing the extension of the spring for weights between 0 newtons and 4 newtons. So the weight is up the side, and the extension in centimetres is along the bottom. Calculate the spring constant using information from the graph in the weight range 0 up to 2.5 newtons. So going from 0 up to 2.5, 2.5. So the spring constant, we've got force equals the spring constant times by the extension. So we need to rearrange that to find the spring constant. So we'll use the magic triangle, draw the triangle, create a top shelf, split the bottom bit into 2 by putting a multiplication sign there. Now, I've got the formula is something times by something, and I've got room for something times by something. So I will put them in there. And I've got one space and one thing, so shove the thing in the space. Now, cover up what you're looking for, and what you're left with is how to work it out. So we're looking for K, cover up K, that's F divided by X. So K equals the force divided by the extension. And it just says use information from the graph. Right, let's pick somewhere between a range of 0 and 2.5 where it's going to be easy for us to do some mathematics. Well, as you can see, right at 2.5, the extension is 10. So that's going to make the maths easy. Oh, sorry, I've wobbled up a little bit there. My apologies. So the force is 2.5 newtons and the extension is, right, what did I tell you before? They don't want it in newtons per centimetre, they want it in newtons per metre this time. So I'm not going to put 10 centimetres, I'm going to put 0.1 metres. Because remember, to convert from centimetres into metres, you divide by 100. So 10 centimetres divided by 100 centimetres per metre. That's going to give you how many metres you've got, so 0.1 metres. Now, that's easy then. Dividing something by 0.1, that just makes it 10 times bigger. So the answer is 25 newtons per metre. Now watch, I could have actually picked any value. What if I'd picked 2, a weight of 2? Right. Well, the extension is 8 centimetres. So if I did the force, 2 newtons this time, and I divide that by the extension, which is 8 centimetres. Now 8 divided by 100 is 0.08. And if you do that, it comes out as 25 newtons per metre. So because it's a straight line, it shouldn't matter what value you pick in newtons and its corresponding value for the extension in centimetres. It should always come out as 25. Try it. Part 2. Describe how the extension of the spring changes as the weight increases from 0 up to 4. So from 0 up to 4. Right. Well, you can see it's linear at first, and then it's curved. That's what's happening to the graph. So at first, the straight line means that the weight and the extension is proportional to each other, and then the curved bit means it's not proportional toward the end. Linear means as one thing gets bigger, the other thing gets bigger. Straight line graph, and then curved graph. Question C. A different spring is stretched. The work done to stretch this spring is 4.2 joules. So that's work done, and that also equals the energy transferred. This spring has a spring constant of 23 newtons per metre. That's K. Calculate the extension of this spring. That's X. Use an equation selected from the list of equations at the end of this paper. So, we're looking for something that's either got work done or energy in it, and K and X. There we are. Energy is a half K times by X squared. Energy transferred in stretching is a half times by the spring constant times by the extension squared. It's just the extension that's getting squared. Now, we need to rearrange it to find X squared. Now, although a magic triangle, a triangle only has 3 corners, you can actually use it when an equation's got 4 things in. Watch. Once again, set up the magic triangle. Make it a bit bigger this time because I've got more things to put in it. Right, always do my top shelf. Now this time, I'm going to have 3 things on the bottom. So do 2 multiplication signs. Now I've got something times by something times by something squared. And I've got room for something times by something times by something. So just shove them in. And I've got 1 space and 1 thing, so shove that in there. Now, like before, cover up what you're looking for. So we're looking for X squared. Cover that up. And what you're left with is how to work out X squared. So X squared is going to equal E divided by a half times by K. Now remember, that's not X yet though, that's X squared. And that's going to come out as 0.3652. Now, if we want X, we're going to need to square root both sides. So the square root of X squared will be the same as the square root of that. Now, this square root will cancel out with the square, and that'll just leave X. So X will be the square root of 0.3652, and that'll equal 0.6043. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.